Hey guys, today's lesson is on section 4.5b over change of variables for definite integrals. The change of variables is just the U substitution technique that we looked at in 4.5a. The only difference here is that we're doing it for definite integrals rather than indefinite integrals. So that's the only change here, the definite part, okay? And we're going to be looking at the 4.5b notes, which you should have in front of you. If you don't have them, you can download them from the website. They look like this. We're going to be running through example 1 and example 2 there. So let's start with example 1 and evaluate this definite integral. The definite integral of x times x squared plus 1 cubed dx from 0 to 1. So again, the only thing different about this is instead of doing an indefinite integral, this is a definite integral, and I know that because of the lower and upper bounds. And we don't normally do this, but when I'm doing a change in variables, when there's two different variables involved, in our case x and then the u, and I've got these lower and upper bounds, I like to remind myself what they are, and these are actually x values. This is x going from 0 to 1. Okay? And so the technique is similar to what we learned for indefinite integrals. We pick an inner function, a u. In this case, x squared plus 1 would be our best choice because it's inside this cubed function. And really anything that's in parentheses is kind of is likely going to be our inner function. So u equals x squared plus 1. Now I'm going to rewrite everything, but just replace the x squared plus 1 with a u. So definite integral of x times u cubed now dx, x going from 0 to 1. Okay, and same situation as before. We've got the dx here. We can't integrate until all our variables match up, so we need to get rid of this x and this dx. We're going to start with the dx and see if that takes care of things. So we go back to this equation, which relates u and x, and we're going to use it to get an equation that relates du and dx. And we do that by finding du dx, the derivative of u with respect to x, which in this case is 2x. We can kind of shuffle that algebraically, solve it for dx. We get dx equals du over 2x. All right? And so we take that, that's what dx is equal to. We take that and we substitute it in for dx. So I'm going to rewrite everything, but now swap out the dx with du over 2x. So definite integral of x times u cubed times du over 2x. Again, going from x is 0 to x is 1. I can cross out the x. That's an x in the numerator and x in the denominator. This is all just being multiplied, so that simplifies. We've seen that situation a lot. And I can actually write that du over 2, I can write that as a 1/2 times du. So that 1/2 is just a constant that I'm going to pull out front. So I've got 1/2 u cubed du. I'm going to scroll down here just a little bit. And again, this is going from x is 0 to x is 1. Now at this point, you actually have two options, and I'm going to show you guys two ways to do this. and you can decide which way you want to do it. There's kind of a preferred way and then another way. I'm going to do it both ways. So I'm going to split this into two parts here. And I'll scroll down just a little bit. So I'm going to make a wall here between my two parts. The first one, I'm just going to find this indefinite integral. Okay, I'm gonna find just the antiderivative of 1/2 u cubed du. So that would be 1/2. Let's see, that's 1/2 is a constant. The u cubed, antiderivative of that is 1/4 u to the 4th plus c, right? And I'm doing that from, again, x equals 0 to x equals 1. Scroll down just here just a little bit. So this is 1/8 u to the 4th plus c from x equals 0 to x equals 1. What I want to do, before I use the fundamental theorem and put in the x values, I can't put them in for u because these are x values. I've got to replace my u with what it is in terms of x, just like we did in the indefinite interval problem. So you can see up here, u equals x squared plus 1. I'm going to replace the u with an x squared plus 1. And I'm going to go ahead and simplify it while I'm doing this. So 1/8, that's the 1/2 times the 4th, times x squared plus 1, that's the u to the 4th plus c. So I'll replace the u with a c. That's the technique that we did before, and I'm doing this from x equals 0 to x equals 1. Now I apply the fundamental theorem. Let's scroll down here just a little bit more. Apply the fundamental theorem, and this here is my sort of capital F of x, my antiderivative, right? Fundamental theorem says I do this, evaluate it at 1 minus evaluate it at 0. So antiderivative at 1, antiderivative at 0. So I'm going to go ahead and do that. 1/8 1 squared plus 1 to the 4th. The plus c's always cancel, so I'm not going to worry about the plus c's. Minus 1/8 times 0 squared plus 1 to the 4th. All right, so this is 1/8 times 2 to the 4th minus 1/8 times 1 to the 4th. Almost done here. 2 to the 4th is 16. All right, so this is 1/8 times 16 minus 1 to the 4th is 1, so minus an eighth. So 16/8 minus 1/8, that is 15/8. Okay, that's our answer. And you can do it that way. That's a perfectly acceptable way to do it. It's just that's a little longer than the preferred method. We don't have to have quite as many steps here. So I'm going to scroll back up and go to where I sort of split off here. I'm going to do it a slightly different way.